Hello, in this lecture we'll talk about RISC-V floating-point instructions. So RISC-V has three optional extensions, F, D, and Q modes, to handle single, double, and quad precision floating-point numbers, 32-bit, 64-bit, and 128-bit. It, in these extensions, defines 32 floating-point registers. Their width is the highest precision necessary. So, for instance, if quad precision is implemented, the registers are 128 bits wide, and single precision numbers are stored in the bottom 32 bits of that 128-bit register. There are 32 registers used for floating-point numbers. There are some temporary registers, saved registers, argument registers, more argument, more saved, and more temporary, just like in regular RISC-V. The floating-point instructions have an S, Q, or D appended to indicate the precision. So, for instance, fadd.s indicates a floating-point addition of two single precision numbers. The arithmetic operations include add, subtract, divide, square root, minimum, and maximum, and a variety of multiplication with addition. So multiply and add, multiply and subtract, negative multiply and add, negative multiply and subtract. And we'll come back to those in a little bit. There's also floating point move instructions to move between two different precisions. So for instance, you could convert a double precision number to a single precision. Conversion there as well. Comparison, to compare the values of floating point numbers, and various things to deal with classification and sign injection of the numbers. So floating point multiply add is one of the most critical instructions for signal processing programs. These programs typically involve keeping a running sum of products. So they multiply two things together and add it to the running sum, and you get instructions like fmadd.f of f1 equals f2 times f3 plus f4. These instructions require 4 registers, so we'll need a new instruction format. Here's an example of a floating point program. Again, we're going to add 10 to the scores array for 200 elements in the array. So this program starts out like we've seen before. We'll initialize S1 is the value of I. We'll initialize it to 0. T2 will set to 200. That'll be our comparison. And T0 will be the value 10 that we want to add. But this 10 now needs to be a floating point number. So we'll do a convert from integer, W type, to single precision to convert the 10 in T0 into a floating point number 10. Now we have our for loop. We've already done the initialization. We need to do the comparison. So if I is greater than or equal to 200, we are done. We go down here. Otherwise, we do the body. And to do the body, we need to find the address to read from. So we'll take I and multiply it by 4 by shifting left, and then add it to the base address, and that will give us the address of scores of I. Then we'll do a floating point load word from that address into floating point temporary register 1. Now we'll do a floating point add single precision to add scores of I to 10 and put the result back in FT1. And then we'll do a floating point store word to store floating point temporary register 1 back into the memory address. Then we'll increment I and jump back to the for loop to repeat. So these floating point multiply add instructions need a new type, R4. The other instructions can use the regular R, I, and S types that we've seen before. But for floating point multiply add, we have our op funct3, we have source 1, source 2, and then we use some of the upper bits to hold source 3. And we have a destination, and then a 2-bit funct2 code to say what kind of multiply add we're doing.